Tonight, we drift into one of the oldest and most mesmerizing forces on Earth: fire. It is both a destroyer and a creator, a flicker of warmth and a storm of chemistry. Long before cities, before language, before the first words for light or heat, there was fire, whispering in the dark and shaping the course of human history. It has lived in our myths, our machines, our stars, and our hearts. Fire is not a thing, but a transformation, a living border between what was and what will be. It moves like a thought, consumes like time, and glows with the same energy that powers the stars above us. The same physics that turns a log to ash also fuels the brilliance of the sun. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the gentle light of fire warm your thoughts. Let's begin. Fire is a chain reaction made visible to the human eye. Fire is not a single thing, but a process unfolding at breathtaking speed. Molecules of fuel and oxygen meet, break apart, and recombine, each reaction releasing enough energy to ignite the next. That constant renewal creates the shimmering light we see. What looks like a steady flame is actually millions of chemical transformations happening every second. As bonds break, electrons shift to new arrangements, releasing heat and photons that reach our eyes as radiance. The flame dances because the surrounding air is always moving, altering the balance of fuel, oxygen, and heat. Too little of anyone, and the chain collapses. Too much, and it flares violently before fading. The gentle flicker of a candle and the roaring wall of a wildfire are governed by the same chemistry. Fire is the visible signature of matter transforming itself, showing how energy moves through the world in pure motion. A flame is a boundary where chemistry turns into light. Between the unburned air and the hot gases of combustion lies a razor-thin frontier where molecules are destroyed and reborn. Within this luminous skin, atoms rearrange at astonishing speed, trading bonds and releasing photons. The light comes from particles so small that they exist only for moments, glowing as they cool and vanish. The flame's color changes with temperature and with the elements inside it, painting the boundary in blues, yellows, or white heat. The shape of the flame reveals the balance between energy and motion, where convection lifts hot air upward and pulls in new oxygen from below. In that slender region, matter gives up its stored energy, turning the invisible into the visible. What we see as light is the final expression of chemistry reaching completion, the bright skin of transformation glowing in air before it dissolves back into darkness. Combustion is matter rearranging itself through heat and motion. When something burns, it is not disappearing but changing form. The fuel's atoms combine with oxygen to create new molecules, mostly carbon dioxide and water vapor, while releasing the energy that held them apart. That energy rushes outward as heat, sound, and light, driving the next instant of the reaction. Each molecule that reacts transfers energy to its neighbors, a microscopic relay that continues until the available fuel is gone. What remains is ash, the fraction of material that cannot take part in the exchange. In the glow of combustion, chemistry becomes visible, revealing the hidden restlessness of matter. The same principles that drive a candle flame govern the engines that move our world, and the fires that shape landscapes. Every burst of heat is a small act of creation, an endless rearrangement of the building blocks of reality itself. The color of a flame reveals the elements being consumed. When a substance burns, its atoms release energy in precise amounts, and those amounts decide what color we see. Sodium burns bright yellow, copper creates green or blue, and strontium glows deep crimson. These colors come from electrons jumping between energy levels and releasing photons of exact wavelengths as they fall back. The spectrum of light from a flame acts like a fingerprint for the elements inside it, allowing scientists to identify materials by their colors alone. In fireworks, this principle becomes art, as metal salts are carefully chosen to paint the sky with color. Even in a simple candle flame, a rainbow exists. The blue near the base marks complete combustion, while the yellow glow above comes from carbon particles radiating heat before they vanish. Each hue tells a story of atoms giving up their energy, shining briefly before they change forever. The hottest part of a candle flame hides just above the wick. The familiar candle flame seems simple, but its heat is unevenly distributed. The region just above the wick, where vaporized wax mixes with oxygen, burns the hottest. Here, temperatures can reach over 1,000 degrees Celsius. The lower blue edge marks where the reaction is most complete, while the yellow and orange glow higher up comes from cooler carbon particles radiating light before they fade. The wick itself remains mostly unburned because wax vapor draws the flame upward, away from the thread of fibers. If the balance shifts and oxygen flows poorly, the flame flickers and smokes. In perfect conditions, it forms a steady teardrop, a small engine of chemistry converting wax into carbon dioxide, water vapor, and light. The heat we feel on our hands is energy once trapped in molecules, now freed to move through air as warmth and glow. Blue flames are nearly twice as hot as orange ones. A blue flame marks a perfect balance of fuel and oxygen, where nearly all molecules burn completely. Because no carbon particles remain to glow yellow, the flame shines with pure thermal light from excited molecules at very high temperatures. The color blue itself corresponds to higher energy photons, meaning the reaction releases more energy per collision. Gas stoves and torches burn blue because the air supply is carefully controlled, producing steady heat ideal for cooking or welding. Orange flames, in contrast, come from incomplete combustion, where glowing soot particles radiate at cooler temperatures. Their beauty lies in the visible carbon that blue flames have already consumed. The difference between the two is the measure of efficiency and precision in combustion. Blue fire burns cleanly and fiercely, a sign of balance so complete that almost nothing is left behind but heat, light, and invisible gas. Some flames burn so cool they can briefly touch skin without harm. Not all fires blaze with intense heat. In special conditions, such as when alcohol burns with limited oxygen or when certain fuels produce weak reactions, flames can exist at surprisingly low temperatures. These cold flames glow faintly blue and can stay below 200 degrees Celsius, cool enough to touch for an instant, before causing pain. The reaction occurs slowly, releasing energy over time instead of in violent bursts. Scientists study these flames to understand how combustion begins and how to prevent explosions or engine knock. They show that fire can exist along a wide spectrum of temperatures, from gentle oxidation to plasma-level fury. Even when cool, the process remains the same, atoms exchanging energy through chemical change. These ghostly flames remind us that fire is not defined by heat alone, but by transformation itself, the quiet rearranging of matter in light. Fire can exist in almost any gas if fuel and oxygen are perfectly balanced. Although oxygen is the most common supporter of combustion, it is not unique. Many gases, from fluorine to chlorine, can sustain fire if the right fuel is present. What matters is balance. The proportion of reactants and the energy needed to break their bonds. Too little oxidizer, and the flame dies for lack of breath too much, and it consumes itself in a flash. In laboratories, scientists have created flames in atmospheres of hydrogen fluoride or pure chlorine, each with distinct colors and behaviors. Some glow green or violet, others nearly invisible. These exotic fires reveal that combustion is a universal language of chemistry, dependent only on the ability of atoms to exchange electrons. Wherever energy can be released through bond breaking and reforming, fire can appear, even in environments far removed from the gentle air that feeds our familiar flames. What fire consumes it also transforms into entirely new substances. Burning is a process of creation as much as destruction. When wood burns, cellulose breaks down into gases, ash, and charcoal. Hydrocarbons in the fuel combine with oxygen to form carbon dioxide and water vapor, releasing energy in the process. The flame is both the cause and the evidence of this transformation. Every wisp of smoke carries molecules that once formed part of something solid. Even the minerals left behind in ash are rearranged remnants of the original material, altered by heat and exposure. In this way, fire acts as an agent of change, converting complex organic matter into simpler, more stable forms. Nothing vanishes. It simply shifts into new arrangements of atoms. What was once structure becomes energy, and what was once energy becomes warmth and light. Through fire, matter writes new chapters of itself in the language of chemistry. The crackle of burning wood comes from moisture flashing into steam. Inside every piece of wood, even one that feels dry, tiny pockets of water hide between fibers. As the heat of the flame reaches them, that water expands instantly into steam, building pressure until it bursts through the wood's surface. Each pop or crack is the sound of those miniature explosions. At the same time, sap and trapped gases add their own voices, snapping as they escape. The result is a living soundscape, a reminder that burning is not silent transformation, but a physical struggle within the material. As the wood continues to heat, it releases volatile gases that feed the flame, turning solid matter into fuel. The rhythm of crackling logs reflects the balance between moisture, heat, and release. The final dialogue of a living substance returning its stored energy to the air as warmth, light, and sound. Sparks are tiny particles of metal glowing from intense oxidation. When a spark flies from a fire or grinding wheel, it is a speck of metal heated so quickly that it glows before vaporizing. As the particle leaves the main flame, oxygen in the air attacks its surface, creating a miniature fireball of oxidation. The heat generated by this reaction is immense compared to the particle's size, often exceeding temperatures that melt steel. The bright trail it leaves is the light of atoms losing electrons and forming oxides. In fireworks, sparks are carefully engineered, with metals like iron, titanium, and aluminum chosen for their color and burn time. Even the sparks from a campfire follow the same principle. Tiny fragments of fuel lifted into the air by rising heat, each completing its own brief combustion. Every spark is a microcosm of the larger flame, a self-contained burst of transformation that lasts only an instant. The shimmer above a flame is air bending light as it heats. Above every flame, the air ripples like a mirage. The heat rising from combustion changes the density of the surrounding gas, and as light passes through it, the shift in density bends the rays in unpredictable ways. Our eyes perceive the bending as a shimmer or distortion, like waves of transparency. The hotter the air, the greater the effect, because heat makes molecules spread farther apart, creating layers of different refractive indices. This same principle causes the road to appear wet on a hot day, or a desert horizon to waver in illusion. In laboratories, scientists use lasers to study these shimmering patterns to understand how heat moves through air. What looks like a soft halo of movement is really a signature of convection, the visual language of air translating invisible temperature gradients into motion and light. Flames flicker because rising air keeps reshaping the reaction. A flame is not a fixed shape, but a moving balance of chemistry and air. As hot gases rise, cooler air rushes in to take their place, feeding the fire with fresh oxygen while disturbing its form. This creates small pockets where the fuel-to-air ratio shifts, causing the flame to dance and pulse. Even the tiniest movement in the surrounding air alters how heat spreads and how fast molecules collide. In still environments, like in a sealed chamber or in microgravity, flames can hold steady without flicker, revealing their true spherical nature. But in the open air, convection currents constantly sculpt the flame, making it breathe and move like a living thing. The flicker we see is the visible expression of equilibrium being tested and re-established again and again. It is the heartbeat of fire, responding endlessly to the air around it. Candlelight forms from glowing carbon particles before they vanish. Inside a candle flame, wax vapor rises and reacts with oxygen, breaking into carbon and hydrogen atoms. The hydrogen burns cleanly, producing heat and water vapor, but the carbon lingers longer, forming tiny particles called soot. These microscopic bits of carbon are heated until they glow, releasing the warm yellow light we associate with candlelight. As they rise through the flame, they are eventually consumed, leaving behind only gas and faint traces of ash. This process creates a gradient of temperature and chemistry, from blue at the base where complete combustion occurs, to golden hues near the top where particles shine and disappear. The light of a candle is not from fire alone, but from matter on the edge of vanishing, each carbon particle glowing for a heartbeat before dissolving into the air. The flame's beauty lies in that final instant of transformation. The shape of a flame is drawn by the speed of the surrounding air. A flame's form depends entirely on how quickly air moves around it. In calm conditions, the hot gases rise straight upward, creating the familiar teardrop shape. When air moves faster, the flame stretches, bends, or flickers sideways. The smooth contour is the visible outline of convection, where warm air rises and cooler air rushes in to replace it. If the airflow becomes turbulent, the flame breaks into chaotic forms, twisting into waves or torn edges. Engineers and scientists study these shapes to understand combustion efficiency, because every curve reveals how heat and oxygen interact. In zero gravity, where air no longer rises, the flame becomes perfectly spherical, shaped only by diffusion. The geometry of fire is therefore not random, but sculpted by motion, a constant interplay between chemistry and the invisible currents of the air that feed its breath. Fire can produce sound as pressure waves vibrate the air. Every flame generates subtle fluctuations in air pressure. When combustion happens rapidly, the expanding gases create waves that move outward as sound. The crackle of a campfire, the roar of a furnace, and the low hum of a gas flame are all different expressions of this same phenomenon. Each sound depends on how fast the gases expand and how irregularly they escape. In large fires, these vibrations can become so strong that they create deep, resonant tones, sometimes called fire whirls or combustion oscillations. Scientists study these sounds to monitor stability in engines and rockets, where flame-driven pressure waves can become dangerous. Even a quiet candle hums faintly, though too softly for human ears. Fire has a voice because it moves the air that surrounds it, translating chemical energy into vibration, turning heat and light into a music of pressure and motion. Plasma within a flame can conduct electricity like a weak wire. At high enough temperatures, the atoms in a flame become partially ionized, freeing electrons that can move through the gas. This creates plasma, the fourth state of matter, which behaves both like a fluid and an electrical conductor. Though the effect is weak in ordinary fire, it can be measured with sensitive instruments. Electric fields can bend or stretch a flame, proving that charged particles are present within it. In plasma torches and lightning, this conductivity grows powerful enough to cut metal or light up the sky. In a candle flame, the same principle exists in miniature, a whisper of the same process that powers the sun. Fire, in this sense, bridges chemistry and physics, existing halfway between matter and energy. Its plasma core carries current softly through the air, linking each burning molecule in a web of light and motion. Fire behaves differently in every gravity environment. Gravity shapes how hot gases move. On Earth, it pulls cooler air downward, while lighter, hotter gases rise, creating the familiar flickering flame. In weaker gravity, such as on the Moon or Mars, convection slows, and flames grow wider and dimmer. Without gravity to drive air circulation, combustion depends more on diffusion, the slow mixing of molecules. In orbit, where weightlessness dominates, flames become spheres, glowing evenly in all directions, with no flicker at all. They burn at lower temperatures, but consume fuel more efficiently because the chemical reactions spread uniformly. These changes reveal how dependent ordinary fire is on gravity's pull. Researchers study such flames in spacecraft to understand fire safety and combustion science in extreme conditions. The behavior of flame across different gravities reminds us that even something as familiar as fire is shaped by the invisible geometry of force and flow. In zero gravity, flames become perfect spheres of light. In the absence of gravity, the hot gases produced by combustion no longer rise, and cold air does not sink to replace them. Instead, the reaction spreads equally in all directions, forming a luminous orb that seems to hover in place. These spherical flames burn slowly, often with a dim blue color, as diffusion rather than convection delivers oxygen to the fuel. Because the process is so gentle, the flame's chemistry becomes unusually efficient, converting nearly all the fuel into water vapor and carbon dioxide with very little soot. Astronauts aboard the International Space Station have observed such flames, describing them as eerily calm, like floating stars. These perfect globes reveal the true nature of fire when freed from the turbulence of air currents. They are not chaotic, but serene, quiet spheres of chemistry sustained by balance alone. Fire can continue to burn in pure oxygen without any visible color. In an atmosphere of pure oxygen, combustion becomes so complete that it can lose its visible glow. Without unburned carbon particles or incomplete reactions to produce yellow or orange light, the process releases energy primarily as heat and ultraviolet radiation, which the human eye cannot see. The result is a nearly invisible flame, capable of extraordinary temperatures. Such conditions are dangerous because fire becomes hard to detect, even as it consumes material rapidly. Experiments with oxygen-rich environments are conducted only under strict safety controls, since even a small spark can trigger explosive reactions. This kind of colorless combustion demonstrates that light is not an essential part of fire, but a byproduct of imperfection. When chemistry proceeds flawlessly, the reaction becomes silent and unseen, a pure exchange of energy that reveals how close fire can come to invisibility. Some metals burn hotter than molten rock. Metals are not usually thought of as fuels, yet when finally divided or exposed to extreme heat, many can ignite. Magnesium, titanium, and aluminum all burn with brilliant white or blue flames, reaching temperatures that surpass the melting point of basalt or granite. Once started, these reactions are nearly impossible to stop because the metals react directly with oxygen, forming stable oxides that release enormous energy. In welding and pyrotechnics, this intensity is harnessed deliberately, but in industrial accidents, it becomes destructive, melting through containers and floors. Underwater, certain metal fires can continue to burn, fueled by their own stored energy. These flames remind us that combustion is not limited to wood or oil, but a universal process tied to the way atoms exchange electrons. When metals burn, they reveal the raw power locked inside matter itself. Lightning can fuse sand into glass in a single flash. When a bolt of lightning strikes sandy ground, the heat can exceed 30,000 degrees Celsius, hotter than the surface of the sun. In that instant, the grains of silica melt and fuse together, forming hollow tubes of natural glass called fulgurites. These fragile, branching structures preserve the path of the lightning as it traveled through the earth, sometimes stretching meters deep below the surface. Each fulgurite is unique, a frozen record of an event lasting less than a second. Scientists study them to understand the electrical and thermal effects of lightning, while collectors prize them for their delicate beauty. The process that creates them mirrors the way humans make glass, only on a far faster and more violent scale. In a single flash, nature performs its own act of artistry, turning ordinary sand into shimmering glass born of fire and storm. A bolt of lightning can heat the air to 5 times the temperature of the sun. The core of a lightning strike reaches around 30,000 degrees Celsius, while the surface of the sun averages only about 6,000. This unimaginable heat occurs as electrical energy rips through the atmosphere, forcing electrons to tear free from atoms. The rapid expansion of this superheated air creates the shockwave we hear as thunder. In less than a second, molecules are broken, rearranged, and scattered, leaving behind a narrow channel of plasma that glows brilliant white. The surrounding air cools just as quickly, collapsing inward with a rush that deepens the thunderclap. Lightning's power demonstrates the immense energy stored in the sky's electric fields, released in a heartbeat. Though the strike lasts only a fraction of a second, its brightness and heat transform everything in its path, a reminder that even air itself can burn under the right conditions. There are flames that can burn underwater when fueled by special chemicals. Some chemical reactions release enough oxygen internally to sustain combustion even when submerged. Compounds containing chlorine or fluorine can oxidize metals like magnesium and lithium, producing intense light and heat while surrounded by water. These underwater flames appear almost supernatural, their light diffused through clouds of bubbles. Naval engineers have studied them for emergency flares and underwater welding, where oxygen from the reaction replaces what the water would otherwise smother. The key lies in chemistry, not air. As long as fuel and oxidizer are present together, fire can exist anywhere. These reactions illustrate that burning is not tied to the open atmosphere, but to the exchange of energy at the atomic level. Even beneath the surface of the sea, matter can still transform, releasing its stored energy as light that glows briefly against the dark water. White phosphorus can ignite on its own at ordinary room temperatures. Among the strangest substances known, white phosphorus is so reactive that it bursts into flame when exposed to air. Its atoms are arranged in a strained, unstable structure that seeks release by combining with oxygen. When that reaction begins, the material glows faintly in the dark before igniting into bright yellow fire, producing dense white smoke of phosphorus pentoxide. Because it burns at low temperatures and continues until completely consumed, white phosphorus must be stored underwater or in inert gas. It has been used in flares, incendiaries, and tracer ammunition, though its volatility makes it hazardous. Even without flame, it can emit a soft greenish light known as chemiluminescence. The ease with which it catches fire demonstrates how unstable certain chemical bonds can be, showing that sometimes the mere presence of air is enough to unleash combustion. Volcanoes in Indonesia burn with bright blue fire from sulfur gases. On the slopes of Kawah Ijen in Java, burning sulfur releases an eerie electric blue glow that spills across the volcanic crater. The flames are invisible by day but blaze brilliantly at night, as molten sulfur ignites when exposed to oxygen at temperatures above 360 degrees Celsius. The phenomenon looks otherworldly, as rivers of blue fire flow alongside the molten rock. The color comes from the combustion of sulfur dioxide, a gas that burns hotter and with a different spectrum than ordinary flames. Miners working near the crater once collected solid sulfur for industry, walking among these glowing streams. The site demonstrates how volcanic heat transforms simple elements into vivid displays of light. This blue fire is one of Earth's most haunting natural spectacles, proof that combustion can take unexpected and mesmerizing forms when born from the planet's depths. Meteor trails are miniature fires tracing through the atmosphere. When a meteoroid enters Earth's atmosphere, friction with air molecules heats its surface to thousands of degrees. The intense energy causes the rock or metal to vaporize, creating a glowing trail of plasma and molten particles. The streak of light we call a shooting star is actually this brief combustion of material and air, lasting only a second before fading. Larger meteors can produce bright fireballs, leaving ionized trails that linger as glowing lines in the night sky. The colors vary depending on composition, with magnesium burning white, sodium yellow, and nickel green. Though most meteors disintegrate entirely, some survive the descent to become meteorites on the ground. The burning trail they leave behind is a reminder that even in the thin upper atmosphere, fire can exist, born from the meeting of cosmic speed and earthly air. Wildfires can move faster than a sprinting human. Driven by wind, slope, and dry vegetation, wildfires can race across landscapes at astonishing speed. Under extreme conditions, they may travel more than 20 kilometers per hour, fast enough to outrun people on foot. The heat from the flames preheats nearby fuel, drying and igniting it before the fire even arrives. Embers carried by the wind can start spot fires kilometers ahead, creating a front that expands uncontrollably. The roar of a wildfire is the sound of millions of combustions merging into one vast reaction. Scientists study their movement through models and satellite data to predict behavior and protect communities. Despite their danger, wildfires also serve ecological roles, clearing old growth and returning nutrients to the soil. Their power lies in the sheer scale of chemistry unleashed across the open air, where wind becomes both accomplice and architect of destruction. Fire tornadoes can rise taller than city buildings. Under the right conditions, a wildfire or industrial blaze can form a rotating column of air and flame known as a firewhirl. As heat rises rapidly, surrounding air rushes in from all sides, spinning faster as it narrows into a vortex. The result is a fiery spiral that can reach hundreds of meters high, moving unpredictably across the ground. Inside, temperatures can exceed 1,000 degrees Celsius, and winds can surpass those of hurricanes. Fire tornadoes are rare but immensely powerful, able to lift debris and spread burning embers far from their origin. Though they appear chaotic, they obey the same physics as ordinary whirlwinds, formed by convection and rotation amplified by intense heat. When nature's air currents and fire's energy align, the atmosphere itself becomes a sculptor, shaping columns of flame that tower against the sky. Flames can burn sideways when driven by hurricane winds. In the presence of extreme wind, the familiar upright shape of fire collapses, bending low to the ground as air rushes past. The speed of the wind feeds oxygen faster than convection can lift the hot gases, forcing the flame to tilt horizontally. This phenomenon can occur during wildfires or powerful storms, when winds whip through dry landscapes. The flame behaves like a living ribbon, crawling across the surface rather than rising above it. Even rain cannot stop such fires if the heat remains intense enough to evaporate moisture instantly. Firefighters must account for this behavior when predicting spread, as horizontal flames ignite new fuel far beyond the usual reach. The sight of sideways fire captures the raw interaction between motion and heat, showing how the elements can reshape one another under nature's most turbulent conditions. Firestorms can create their own thunderclouds and lightning. In the most intense wildfires, rising heat forms massive columns of air that behave like volcanic plumes. As the hot gases rise, they cool and condense moisture, forming towering clouds known as pyrocumulonimbus. Within these clouds, particles of ash and ice collide, building electric charge, just as in ordinary thunderstorms. Lightning flashes above the blaze, sometimes igniting new fires miles away. Winds swirl violently as air rushes toward the base of the storm to replace the rising column, feeding the inferno even more oxygen. These self-sustaining systems can generate winds stronger than hurricanes and temperatures that rival volcanoes. Entire weather patterns emerge from the fire's own energy, creating rain, hail, and lightning, all born from combustion. A firestorm is not only an environmental event, but an atmospheric engine, capable of shaping the weather above it through the sheer power of heat rising into the sky. The hottest flames on Earth exceed 3,000 degrees Celsius. Under controlled conditions, flames can reach astonishing temperatures far beyond what most natural fires achieve. Acetylene torches, for example, can burn hotter than 3,000 degrees Celsius when mixed with pure oxygen, hot enough to melt steel and vaporize glass. Some chemical reactions, such as burning magnesium or thermite mixtures of aluminum and iron oxide, produce even more heat, glowing bright white as they tear through metal. These extreme flames are used in welding, cutting, and industrial manufacturing, where precision and power demand temperatures higher than any volcano. At such heat, matter becomes a fluid of electrons and ions, radiating energy across the visible spectrum. The air around the flame shimmers violently as molecules are torn apart. While dangerous, these controlled fires reveal the outer limits of chemistry, where the boundary between flame and plasma begins to blur into brilliance. Some laboratory plasmas reach heat greater than the center of the sun. Inside research facilities, scientists create bursts of plasma that reach temperatures in the millions of degrees. In fusion experiments, magnetic fields confine hydrogen atoms so tightly that they fuse into helium, releasing energy as heat and light. For brief moments, these artificial suns burn hotter than any star's core. The plasma glows in vivid blues and purples as electrons move freely through the charged gas. Despite the temperature, the total energy is contained in a small volume, making it safe for study. Such experiments explore the same forces that power the cosmos and could one day provide limitless clean energy. The heat and light inside these chambers are reminders that fire, in its most extreme form, becomes indistinguishable from starlight. At those temperatures, matter behaves like pure energy, echoing the conditions that existed in the first moments of the universe. Fire can melt stone and leave glassy black surfaces. In nature, extreme heat can transform rock into glass. When lava flows over sand or stone, or when lightning strikes the ground, the intense temperature melts the minerals and fuses them into smooth, shiny layers. This process, called vitrification locks bubbles of gas and streaks of ash inside the glassy surface. Ancient hill forts in Scotland and Ireland show walls that have melted together, evidence of fires hot enough to fuse rock during battle or ritual. In laboratory furnaces, similar effects can be reproduced with temperatures above 1,500 degrees Celsius. The resulting black glass holds the memory of fire's passage, frozen in solid form. Each piece tells a story of transformation, of solid matter briefly becoming liquid under heat so intense that it changes the landscape itself. Fire's ability to melt stone shows that even Earth's hardest materials can yield to its touch. Molten metal fires are almost impossible to extinguish with water. When metals like magnesium, sodium, or aluminum ignite, they burn with ferocious heat and react violently with water. Instead of cooling the fire, water splits into hydrogen and oxygen, feeding it further. The result is an explosive reaction that can hurl molten droplets across wide areas. Firefighters use special dry powders, such as graphite or sodium chloride, to smother these blazes by cutting off oxygen and absorbing heat. In industrial settings, molten metal fires are among the most feared because they can melt through floors and machinery. Even concrete can crack and vaporize when struck by such heat. These reactions demonstrate that fire is not merely a surface phenomenon, but a deep chemical process that reshapes materials at the atomic level. In the wrong conditions, water becomes its accomplice, releasing new energy into the very flames it tries to stop. Aluminum dust can ignite explosively when dispersed in air. Finely powdered aluminum, when suspended in air, forms an invisible cloud of fuel waiting for a spark. Each particle has a vast surface area exposed to oxygen, allowing combustion to happen almost instantly once ignited. The reaction releases immense energy, producing shock waves and intense heat. This phenomenon is known as a dust explosion, and it can occur not only with metals but also with organic materials like flour or coal. Factories that handle fine powders install special ventilation and grounding systems to prevent static discharges that could trigger such events. In aluminum plants, a single electrical spark or frictional contact can unleash an explosion powerful enough to destroy an entire room. The danger lies in the combination of chemistry and geometry, where tiny particles turn air itself into fuel. In that moment, the boundary between solid and flame disappears completely. Gasoline vapors can ignite from static electricity alone. Liquid gasoline does not burn until it evaporates, releasing a cloud of flammable vapor. When that vapor mixes with air in the right proportion, even a small spark can cause ignition. Static electricity from clothing, a cell phone, or the sliding of a gas nozzle can be enough to trigger a flash. This is why fuel stations use grounding systems and safety instructions to prevent ignition sources. The energy required to start the reaction is minuscule, yet the result can be devastating. The flame travels almost instantly through the vapor cloud, returning to the liquid surface and setting it ablaze. Once burning, gasoline produces immense heat, feeding itself through rapid evaporation. The lesson from this chemistry is that danger often hides in the invisible. Fire can begin not from large flames, but from the smallest spark, where energy and vapor meet for a single instant. Even snow can burn if mixed with the right chemicals. Under the right conditions, fire can exist even within frozen landscapes. Certain chemicals, such as sodium or potassium, react violently with water by releasing hydrogen gas and heat. When these elements come into contact with snow or ice, the reaction can generate enough heat to ignite the hydrogen, creating flames that seem to rise from the frozen surface. This paradoxical sight defies instinct, yet it follows simple chemistry. The same reactions are used in controlled experiments to teach how exothermic processes work. These burning snows reveal that fire does not depend on temperature alone, but on the energy stored in chemical bonds. When those bonds break and recombine, heat and light appear regardless of the surroundings. Even in the coldest environment, the laws of energy remain unchanged, allowing flame to bloom where ice should rule. Flames can appear green when copper is part of the fuel. When copper or its salts enter a flame, their electrons absorb energy and jump to higher levels before falling back, releasing light in the green part of the spectrum. This creates a vivid emerald glow that stands out against the warmer hues of most fires. The effect is most familiar in fireworks, where copper chloride or copper acetate is used to produce bright green bursts. In laboratories, similar colors appear when copper compounds are heated for analysis. The color depends on the specific compound and the temperature of the flame. Even trace amounts of copper can tint the fire, revealing its chemical fingerprint. The phenomenon demonstrates the intimate connection between light and matter, where atomic structure determines color. Each green flame is a brief glimpse into the quantum behavior of elements, showing how invisible atomic energy becomes visible as beauty. Certain alcohol fires are invisible in daylight. Some types of alcohol, such as methanol or ethanol, can burn so cleanly, but the flame produces little soot and very little visible light. In bright sunlight, these fires are nearly impossible to see, though they still release intense heat. The reaction between alcohol vapor and oxygen creates mostly carbon dioxide and water, leaving no glowing carbon particles to color the flame. This property makes alcohol both useful and dangerous in laboratories and racing fuels, where accidental ignition may go unnoticed. The invisible flame can be detected only by heat or by its faint blue glow in dim light. Firefighters and chemists use thermal cameras or ultraviolet sensors to identify these hidden fires. The purity of the combustion makes them ghost-like, a reminder that not all flames announce their presence. Sometimes, the most complete fires are the hardest to see. The first wildfires began before trees evolved. Long before forests covered the continents, lightning strikes set fire to primitive plants and dry mats of algae on land. These early wildfires consumed small, low vegetation and released gases into the atmosphere, influencing the balance of oxygen and carbon dioxide. Fossilized charcoal from nearly 500 million years ago preserves evidence of those ancient burns. The arrival of trees intensified the cycle, as wood provided denser fuel and oxygen levels rose high enough to sustain massive fires. Wildfire thus predates forests and even the complex ecosystems that depend on them. It has always been part of Earth's rhythm, shaping evolution by selecting for species that could resist or recover from flame. In those early ages, fire began its role as both destroyer and creator, helping sculpt the landscapes where life would later flourish. Lightning was Earth's earliest natural ignition source. Before humanity learned to make sparks, lightning was the only force capable of setting the world aflame. Each bolt carried millions of volts, striking trees, grasslands, and dry peat. The resulting fires transformed landscapes, releasing nutrients and clearing space for new growth. Animals fled or adapted, and plants evolved traits that allowed them to survive or even depend on periodic burning. The ancient atmosphere was rich in reactive gases, making ignition frequent and widespread. Some scientists believe that these natural fires helped shape the planet's chemistry by producing compounds that later contributed to life's development. Every time lightning flashes, it recreates the same ancient process that first connected sky and earth through flame. It remains a living reminder of nature's power to spark transformation, bridging the energy of the heavens with the matter of the world below. Humans learned to keep embers alive long before they learned to spark new ones. Early humans discovered that fire could be preserved even when they did not know how to create it. by covering glowing embers with ash or carrying smoldering sticks from place to place. They kept heat alive for days or weeks. These traveling fires provided warmth, protection, and the means to cook food. Archaeological evidence shows hearths where ancient people maintained coals over long periods, indicating that firekeeping was a vital skill. Only much later did humans learn to strike sparks from stone or create friction fires with tools. The ability to keep embers alive bridged the gap between discovery and mastery, allowing early societies to migrate and thrive in new environments. Each preserved ember was a small seed of civilization, a captured piece of the wild world's energy carried carefully into the unknown. Charred bones in ancient caves show that early people cooked with fire almost 2 million years ago. Archaeological sites in Africa reveal blackened bones and ash layers dating back nearly 2 million years, evidence that early humans not only used fire but understood its potential. Cooking softened meat, made plants easier to digest, and unlocked nutrients that raw food could not provide. This dietary shift supported the growth of larger brains and changed human evolution forever. The traces left in ancient caves show deliberate fire use rather than accidental burning, with repeated heating in the same spots. These hearths mark some of the earliest steps toward technology and culture. Fire became a tool rather than a threat, a companion that shaped human destiny. The glow of those early flames still burns in every meal, every lamp, and every home, carrying forward the light first kindled in the shadows of prehistoric caves. Firelight extended human activity far beyond daylight hours. For most of prehistory, nightfall meant darkness and rest. Fire changed that forever. With light, people could gather, cook, craft, and tell stories long after the sun had set. The flickering glow of torches and campfires created social spaces where communities formed and culture grew. Shadows moved like living shapes across the walls of caves and shelters, inspiring imagination and art. The warmth of the flame kept predators at bay and gave safety in the wilderness. Over generations, firelight became a symbol of knowledge and spirit, a beacon of awareness in a vast world of night. It transformed time itself by extending the day, allowing thought and creativity to continue beyond nature's rhythm. Every spark of human progress began in those hours when darkness met flame, and minds first learned to think by its gentle glow. Campfires were once the only protection against nocturnal predators. In the ancient wilderness, the circle of light from a campfire marked the edge of safety. The scent of smoke and the crackle of flame kept animals wary, while the heat discouraged insects and cold. Early humans gathered close to these small barriers of light, resting with the knowledge that few creatures would dare cross into the glow. Fossilized hearths found near ancient campsites show how groups used fire not just for warmth, but as defense. Even large predators like lions and hyenas avoided open flames. The campfire became a fortress of flickering motion, a living guardian that never slept. Within its radius, humanity began to dream, inventing tools, stories, and songs. Fire did not just protect life, it gave the space for reflection and cooperation that would shape the course of civilization itself. Ancient storytellers may have invented language around shared firelight. For countless generations, humans gathered at night to share warmth and tales. The hypnotic rhythm of flames gave rhythm to words, and gestures mirrored the dance of light. Anthropologists believe that the campfire's circle may have been the first classroom, where elders passed knowledge through spoken story. In that glow, early language evolved from sound into meaning, allowing complex communication to take shape. The interplay of voice, shadow, and emotion turned firelight into a stage for imagination. Every word, every myth, every lesson told by flame carried forward through time, shaping culture and memory. Around those ancient fires, humanity learned not just to speak, but to dream together. The bond between storytelling and fire remains deep within us, echoing through every spark of creativity that still lights the darkness today. Early humans discovered that certain stones could strike sparks when hid together. The discovery of spark-making stones was one of the great turning points in human history. When flint or chert was struck against iron-rich minerals like pyrite, tiny fragments flew off glowing with heat. Those sparks could ignite dry grass or tinder, creating fire on demand. Mastering this technique freed people from dependence on natural flames and embers, allowing them to make fire anywhere. Archaeological evidence of flint tools shows that ancient humans carried specialized stones for this purpose. The rhythm of striking and catching a spark became a ritual of survival. Each success marked the triumph of knowledge over chance. With every new flame, humanity gained control over energy, transforming danger into utility. The spark between stones was more than fire. It was the first expression of human ingenuity, the moment when intelligence met the physics of the earth. The mastery of fire reshaped human evolution by allowing cooked food and warmth. Cooking changed everything. By breaking down proteins and starches, heat made food easier to chew and digest, freeing energy once spent on raw sustenance for brain development and physical endurance. The warmth of controlled flame allowed migration into colder climates, expanding human presence across the planet. Fire also sterilized water and food, reducing disease and improving health. Over generations, it shaped anatomy, behavior, and culture. Social life formed naturally around the shared hearth, where cooperation replaced competition. The mastery of flame thus marks the boundary between instinct and civilization. In its light, humans became creators of their own environment, no longer bound by the rhythms of sun and season. The story of evolution is incomplete without fire, the companion that carried humanity from the wild into the warmth of its own making. Some early cultures believed every flame held a spirit. In the earliest myths, fire was seen as a living being, breathing and moving with its own will. People believed that each flame contained a consciousness or a divine essence that connected the human world to the sacred. Ritual fires were tended with care and respect, fed with offerings of food, oil, or incense. Many traditions saw flame as a messenger, carrying prayers upward in smoke. In temples and hearths, the fire was both a tool and a presence, symbolizing purity, transformation, and renewal. The way it consumed yet created inspired awe and reverence. Even today, the act of lighting a candle preserves that ancient belief in flame as spirit. Across cultures and time, the fire's glow continues to represent life itself, a reminder that energy, warmth, and soul are intertwined in the dance of light. Ritual fires were used to mark seasons and celestial events. Across ancient civilizations, the rhythm of time was kept not only by stars and sun, but by fire. Great pyres and torches were lit at solstices, harvests, and equinoxes to honor the turning of the heavens. These ceremonies carried profound meaning, connecting earthly life with the cycles above. In many cultures, flame represented renewal, its light mirroring the rebirth of the sun or the return of fertility to the land. Priests and villagers gathered in circles of heat and shadow, watching sparks rise like prayers into the night sky. Fire became the medium between heaven and earth, a visible heartbeat of the cosmos. Its glow measured both time and transformation, reminding humanity that existence itself follows the same path as a burning log: ignition brilliance, and slow fading into embers. Through ritual fire, the universe was celebrated as something living, cyclical, and divine. Charcoal was the first engineered fuel created by humans. Long before coal or oil were known, ancient people discovered that burning wood without air produced a lighter, purer fuel. By covering wood with clay or soil and allowing it to smolder, they created charcoal, a black, porous material that burned hotter, cleaner, and longer than its source. This breakthrough revolutionized fire. Charcoal allowed for higher temperatures that could melt metals and fire ceramics. It powered forges, kilns, and eventually entire economies. Archaeological sites show charcoal pits dating back tens of thousands of years, evidence of deliberate control over chemistry. Unlike raw wood, it could be stored indefinitely and transported easily. Charcoal marked humanity's first step toward manipulating matter on purpose, transforming a simple flame into an engineered tool. It was the bridge between the natural and the artificial, where human intention met the hidden science of heat and transformation. The control of fire enabled the first permanent settlements in cold regions. Before mastery of heat, human migration was limited to warmer climates. Fire changed that entirely. With the ability to create and sustain warmth, people could survive winters, store food, and build shelters in previously uninhabitable places. Hearths became the centers of early homes, and the surrounding villages grew around these dependable sources of heat. The stability of fire meant that families could remain in one location through the seasons, cultivating land and raising animals. Archaeologists find ancient hearthstones in the remains of dwellings across Europe and Asia, proof that flame was the foundation of settlement. Beyond survival, fire brought comfort, light, and safety from predators. It allowed humans to turn cold, dark wilderness into livable space. The steady glow inside those first huts and caves marked the beginning of civilization's expansion into the wider, colder world. Pottery was invented when clay accidentally hardened near fire. The story of pottery likely began with accident. Clay left too close to a hearth cracked, darkened, and then hardened into a new and durable material. People soon realized that heat could transform fragile earth into vessels that held water, food, and grain without leaking. This discovery changed daily life. Pottery made storage possible and cooking more efficient, letting communities settle and grow. Over time, firing techniques became more sophisticated, evolving from open flames to enclosed kilns capable of reaching higher temperatures. Decoration followed utility, with painted and carved designs turning containers into works of art. Every ceramic shard unearthed today carries the fingerprints of that first revelation. That fire could not only destroy, but also create. Pottery stands as one of humanity's earliest technologies born from observation and chance, a perfect meeting of earth, water, and flame. Metalworking began when people noticed shiny beads forming in campfire ashes. The first metal may have been discovered by accident. When ancient fires burned over certain rocks, molten droplets of copper or lead sometimes appeared among the ashes. Early humans, drawn to their brightness, began experimenting with these strange materials, learning that heat could extract them from stone. This curiosity gave birth to smelting and the entire field of metallurgy. By building hotter fires with charcoal and air bellows, people transformed raw ore into tools, ornaments, and weapons. Metal reshaped human society, replacing stone with strength and flexibility. The spark of wonder that led to collecting those first glimmers of metal opened the path to modern technology. Each bead found in the coals of an ancient hearth was a tiny revolution, proof that fire could reach deep into the earth and bring out its hidden treasures. Ancient glass was discovered when sand fused in extreme heat. According to legend, ancient merchants discovered glass when cooking over a sandy beach with blocks of mineral soda. The intense heat melted the sand into a translucent sheet, revealing a new substance unlike any other. Whether myth or truth, early glass appeared wherever fire met silica and alkali in the right combination. Natural glass also formed from lightning strikes and volcanic flows, inspiring imitation. Once humans learned to recreate the process deliberately, glass became one of civilization's defining materials. It allowed light to pass while protecting from the elements, turning fire's destructive heat into creativity. Ancient glassmakers were revered as alchemists, masters who could turn earth into clarity. Every window, lens, and vessel today owes its existence to that first moment when someone looked into the pooling sand and saw the miracle of melted light. The first torches were likely resin-soaked sticks from pine trees. Before oil lamps or candles, humans lit their nights with simple torches. Sticks coated in resin-rich sap from pine or birch burned with bright, steady light, carrying the flame from one place to another. These handheld fires illuminated caves, guided hunts, and marked paths through forests. Resin acted as both fuel and glue, holding the ember to the wood and resisting wind or rain. Some of the oldest cave paintings show soot marks along walls, evidence of torchlight guiding artists as they worked deep underground. Over time, torches became symbols of ceremony and knowledge, carried in rituals and processions. Their steady flame represented the continuity of light in darkness. Each one was both tool and symbol, a portable sun that allowed humanity to explore, create, and connect beneath the vast, dark canopy of the prehistoric world. Early lamps burned animal fat and glowed with smoky light. Long before candles, people used shallow stone bowls filled with melted fat to create light. A strip of plant fiber, or moss, served as a wick, drawing the liquid upward, where it burned with a dim but enduring flame. These primitive lamps illuminated the earliest homes, caves, and shrines. The smoke clung to walls, leaving black residue that still stains ancient dwellings today. Though simple, these devices extended the day and made indoor life possible. Archaeological finds show beautifully carved lamps, shaped like animals or adorned with symbols, revealing that they carried spiritual significance as well as practical use. The warmth and flicker of these flames offered companionship against the night. Each small lamp was a contained fragment of the sun, tamed to rest upon a hearthstone, whispering quietly while the world outside lay in shadow. Fire temples once burned flames that never went out. In parts of ancient Persia and India, sacred fires were tended continuously for centuries. These temples were built around flames that symbolized eternal truth, purity, and divine order. Priests guarded them day and night, feeding the fire with precise offerings of wood or oil to maintain its perfect balance. The constant burning represented the unbroken connection between the material and the spiritual world. Worshippers believed that to let the fire die was to break a cosmic link. Some of these eternal flames still exist today, burning from natural gas vents or preserved through generations of devotion. They are among the earliest expressions of humanity's reverence for light as a living force. Within those sanctuaries, the steady glow was more than warmth or brightness. It was the embodiment of continuity, a flame that outlasted empires and carried the memory of belief itself. Mythologies across the world describe gods who stole fire for humankind. The gift of flame appears in countless stories, from Greece to Polynesia to the Americas. In Greek legend, Prometheus defied the gods to bring fire to humanity, suffering eternal punishment for his compassion. In Polynesian tales, the hero Maui stole it from the underworld, while in Native American myths, animals conspired to capture it for the first people. These stories reveal a universal recognition of fire as divine and dangerous. To possess it was to share in the power of creation itself. Fire symbolized both knowledge and rebellion, the spark that separated humans from the rest of nature. The theft of flame became the mythic moment when intelligence and spirit fused, marking the dawn of civilization. Through these legends, every culture acknowledged the same truth, that fire is both a blessing and a burden, forever entwined with the human soul. Wildfire is an ancient part of the planet's life cycle. Long before humans existed, lightning ignited vast forests and plains, setting off cycles of destruction and renewal. These natural fires shaped ecosystems by clearing old vegetation, releasing nutrients, and making space for new growth. Many plants evolved to depend on them, their seeds waiting patiently for heat or smoke to signal the right time to sprout. Even the atmosphere bears the imprint of ancient fire, enriched by gases produced in flames. To modern eyes, wildfire seems purely destructive, but in nature, it is part of balance. Forests and grasslands are living systems that need disturbance to thrive. Fire resets the clock of the landscape, ensuring diversity and regeneration. Each blaze is a chapter in the planet's story, a reminder that creation and destruction have always been partners in the grand rhythm of life. Some plants depend on heat to release their seeds. In fire-prone regions, evolution found a remarkable strategy for survival. Certain plants produce cones or seed pods that remain sealed until exposed to intense heat. When wildfire sweeps through, the heat melts resins or cracks shells, releasing seeds into nutrient-rich ash. This adaptation ensures that new growth begins precisely when competition is lowest and the soil is freshly fertilized. Species like the giant sequoia, lodgepole pine, and banksia thrive on this fiery cycle. Without periodic burning, their reproduction slows or ceases altogether. In this way, fire becomes a partner in life rather than an enemy. The forest burns, but the next generation waits within it, ready to rise from the ashes. Through this bond between flame and renewal, nature turns destruction into opportunity, proving that survival sometimes depends on surrendering to the heat. Certain pine cones open only after being scorched. High in mountain forests and across dry plains, some pine species guard their seeds inside cones sealed with pitch. These cones can hang on branches for years, waiting for fire. When flames pass through, the heat softens the resin, allowing the scales to spread apart and release the seeds. The ground below, now cleared of underbrush and coated in mineral-rich ash, becomes the perfect nursery. This relationship between tree and flame has existed for millions of years. The trees rely on fire not just to reproduce, but to shape the very habitat they inhabit. Without periodic burning, the forest would choke with growth, and the seeds would never find soil to take root. Every pine cone that opens in the aftermath of fire is a symbol of adaptation, showing how life learns to grow through adversity. Grasslands rely on periodic burning to stay fertile. Across the savannas of Africa, the prairies of North America, and the steppes of Eurasia, natural fire acts as a cleansing force. Flames remove dead vegetation, recycle nutrients, and prevent trees from overtaking open plains. After a burn, grasses regrow quickly, nourished by ash and sunlight. Animals return soon after, feeding on the tender shoots that emerge from the blackened earth. Many indigenous cultures recognized this rhythm and practiced controlled burning to maintain balance. Without fire, grasslands would eventually transform into forests, losing the diversity that depends on open space. These ecosystems evolved alongside flame, and their fertility depends on it. Fire is not an intruder here, but a gardener, pruning and feeding the land in cycles older than humanity. The green waves that follow a burn are the Earth's quiet expression of renewal. Lightning strikes start thousands of natural fires every day around the world. At any given moment, lightning is striking somewhere on Earth, igniting countless small fires in forests, deserts, and grasslands. Most extinguish quickly, but some grow into vast blazes that shape entire ecosystems. These events link the atmosphere to the ground in a direct exchange of energy. Each strike carries immense power, heating the air to tens of thousands of degrees in a fraction of a second. When that heat meets dry vegetation, the spark becomes flame. Lightning-driven fire is one of the oldest natural processes on the planet, responsible for maintaining the balance of life long before humans appeared. Modern satellites track these strikes daily, mapping patterns that reveal how weather, climate, and vegetation interact. What begins as a flash in the clouds becomes a force that renews the Earth, reminding us that even destruction has purpose in nature's design. Fire creates nutrients that feed the next generation of growth. When vegetation burns, the organic matter that once held nutrients in complex structures breaks apart, releasing minerals like potassium, calcium, and phosphorus into the soil. These elements dissolve into rain and seep into the roots of new plants. The result is a burst of fertility in the seasons following a fire, often visible as carpets of green across one's blackened land. Even the ash itself acts as a mild fertilizer, balancing acidity and enriching the soil. This natural recycling ensures that nothing in the forest is truly lost. Fire transforms locked-up energy and matter into forms accessible to life again. What looks like devastation is part of a larger pattern of renewal, a planetary metabolism in which flame plays a vital role. Every new sprout rising from charred soil carries within it the memory of the fire that fed it. Ash can neutralize acidic soil and promote new plants. After a fire, the fine gray powder left behind is more than residue. It is chemistry waiting to restore balance. Ash contains alkaline minerals that counteract acidity in the soil, improving conditions for many species of plants. When rain mixes with this mineral dust, it creates a mild solution that seeps deep into the ground, unlocking nutrients and encouraging microbial activity. Farmers have long used wood ash to enrich fields, echoing nature's own cycles. In forests, this neutralization helps seedlings take root in places where the soil was previously too acidic for growth. Even in volcanic regions where eruptions coat the land in ash, the eventual result is renewal. The forest floor, blackened and still, becomes a laboratory of life. From this quiet chemistry emerges new vegetation, proof that even in the aftermath of fire, the earth begins to heal itself. Birds have been seen carrying burning sticks to flush prey from hiding. In parts of Australia and Africa, certain raptors such as black kites and brown falcons have been observed picking up smoldering branches from wildfires and dropping them into unburned areas. This deliberate act spreads the flames, driving insects, lizards, and small mammals into the open where the birds can catch them. Indigenous peoples have known of this behavior for centuries, calling these species firehawks. Scientists who documented it confirmed one of the few known cases of animals manipulating fire as a tool. The sight of a bird wielding flame blurs the line between instinct and intelligence, revealing a cunning adaptation to an ancient force. Fire, in this context, becomes part of the natural hunting strategy, shaping behavior as profoundly as it shapes the landscape. The partnership between predator and flame is one of evolution's most astonishing collaborations. Some beetles can detect the infrared heat of distant fires. Certain species of fire beetles possess extraordinary sensory organs that allow them to detect the infrared radiation produced by forest fires from many kilometers away. They fly toward the heat, not away from it, because freshly burned wood is the perfect place to lay eggs. The larvae feed on weakened trees and charred bark, thriving where other creatures cannot. These beetles are equipped with tiny infrared receptors, so sensitive that they can sense temperature changes smaller than a degree. Their ability surpasses many human-made detectors. In a way, they have evolved to follow fire as others follow water or light. This adaptation ensures their survival in an environment shaped by periodic burning. The beetle's strange attraction to heat shows how deeply fire is woven into the fabric of life, guiding even the smallest creatures through cycles of destruction and renewal. Fire changes landscapes faster than erosion or rain. While wind and water slowly shape the surface of the earth, fire works in moments. A single blaze can alter entire ecosystems, stripping vegetation, exposing soil, and changing the chemistry of air and ground alike. Hillsides blacken, forests open, and new patterns of life emerge within days. In some cases, repeated burning over centuries creates permanent biomes like savannas and shrublands. The rapid transformation caused by fire rivals geological forces in its impact. Yet it operates on a human timescale. Afterward, the landscape does not return to what it was, but becomes something new, shaped by both loss and potential. The speed of this process reveals how energy can remake the planet, reminding us that change need not be slow to be profound. Fire is Earth's sudden sculptor, carving renewal out of devastation. Desert ecosystems use small fires to maintain balance. In the vast dryness of deserts, fire appears rarely but serves a critical role when it does. Sparse vegetation, scattered shrubs and hardy grasses can burn in brief flashes, clearing dead material and encouraging the growth of new shoots. These small fires recycle nutrients into the thin soil, allowing life to persist in environments that seem barren. Many desert plants have thick bark, waxy coatings, or seeds that resist heat, enabling them to survive and regenerate quickly afterward. The animals too have adapted to this rhythm, burrowing underground or fleeing to rocky shelters until the land cools again. By removing old growth and stimulating new life, fire prevents overcompetition for scarce water and sunlight. Without it, the desert could slowly choke in its own dryness. Even here, in one of the world's most fragile ecosystems, fire plays the part of a quiet gardener, keeping balance through renewal. Charred forests cool the soil and trap moisture. After a wildfire passes, the blackened remains of trees might look lifeless, yet they serve a vital purpose. The dark carbon residue left behind forms a thin layer that absorbs rainfall and holds it in the soil. Beneath this charred blanket, roots, seeds, and microorganisms find refuge, insulated from the harsh sunlight above. The burned wood acts like a sponge, slowing evaporation and preserving moisture through the early stages of regrowth. Over time, mosses and fungi colonize the cooled earth, beginning the slow restoration of life. Scientists studying post-fire ecosystems have found that the soil beneath the charred surface can retain more water than unburned areas. This paradox shows how destruction creates conditions for recovery. A blackened forest floor may appear silent and dead, but within it lies the hidden pulse of renewal, waiting patiently for rain and sunlight to return. Fire shapes migration paths of animals across continents. For countless species, the presence of fire determines when and where they move. Grazing animals follow the fresh green shoots that spring up after a burn, finding nourishment in the renewed growth. Birds of prey and scavengers gather at the edges of flames, hunting insects and small animals fleeing the heat. Even large migrations in Africa and Australia often follow seasonal burn patterns, moving in harmony with the cycles of fire and regrowth. Over time, these patterns carve invisible trails across the land, guiding herds, flocks, and predators alike. Fire becomes a map written in light and ash, directing life towards sustenance. It is not only a force of destruction, but a shaper of movement, influencing the rhythm of entire ecosystems. When flames fade, life begins its journey anew, tracing paths first drawn by the flicker of ancient fires across the plains. Smoke particles can seed clouds and influence rainfall. When fire sends plumes of smoke into the sky, it releases tiny particles that drift high into the atmosphere. These microscopic bits of ash and carbon act as condensation nuclei, giving water vapor something to cling to. In time, clouds form around them, thickening into storm systems that can eventually release rain. Some regions even experience increased rainfall downwind of large fires, as the smoke changes the way sunlight and heat interact with the atmosphere. However, not all effects are beneficial. Too much smoke can block sunlight, cooling the air and preventing clouds from forming at all. The balance is delicate, and scientists study these interactions to understand how fire alters climate patterns on both local and global scales. What rises as a sign of destruction can return as a gift of renewal, as rain falls back upon the scorched earth it was born from. Some fungi thrive only on burned ground. Hidden beneath the ashes of a forest fire, certain species of fungi awaken. Their spores can lie dormant for decades, waiting for the intense heat and chemical changes that only fire can bring. Once the ground cools, they emerge rapidly, sending up dark, fruiting bodies that feed on the charred remains of plants and wood. These fungi play a crucial ecological role by breaking down carbonized material and returning nutrients to the soil. Some, like the morel mushroom, even form mutual relationships with burned trees, flourishing in landscapes where other life has barely begun to return. For foragers, the appearance of these fungi signals that recovery has started. In a place that looks ruined, new life is already rewriting the soil's chemistry. Fire may clear the surface, but below it, these resilient organisms turn destruction into fertile possibility. Prairie fires once stretched across thousands of miles. Before human settlement and agriculture, vast prairies of North America burned regularly in immense natural fires that could travel for weeks. Lightning strikes and dry wind set entire grasslands alight. But these fires rarely destroyed the ecosystem. Instead, they renewed it. The grasses evolved to grow back quickly, using deep roots that survived below the heat. Bison, antelope, and countless other species followed the regrowth, feeding on the tender shoots that appeared after the flames. The smoke from these ancient fires carried across horizons, marking the cycle of rebirth that defined the prairie's life. Indigenous peoples understood this rhythm and used controlled burns to mimic it, maintaining balance and abundance. The modern landscape has quieted, but in its soil remains the memory of fire's vast passage, the echo of the element that once brushed its hand across entire continents in golden flame. Savannas evolved to burn regularly without being destroyed. In tropical regions, the combination of grass, trees, and seasonal rain creates ecosystems that depend on frequent fire. Savannas are not devastated by burning, they are renewed by it. The grasses regrow within days, nourished by ash and open sunlight, while trees with thick bark survive and sprout new leaves. Fire prevents dense forest from forming, preserving the wide plains that support elephants, lions, and herds of antelope. Without flame, these landscapes would change entirely, losing their defining character. Scientists studying savannas have found that even lightning alone can maintain this balance. shaping the pattern of life through time. Fire acts as both boundary and sculptor, keeping open what would otherwise close. In every flicker across the horizon lies the quiet collaboration between earth, rain, and flame, an eternal partnership that ensures the land continues to breathe. Ancient lightning fires may have created the first patches of open grassland. Millions of years ago, as the world's climate grew drier, lightning began to strike more often across wooded plains. The fires that followed cleared trees and shrubs, leaving behind open spaces where grasses could thrive. These early burn zones became the cradles of savannas, prairies, and steppes, ecosystems that still dominate much of the planet today. The animals that lived there evolved alongside fire, adapting to grazing and migration patterns shaped by its rhythm. In this way, lightning acted as both destroyer and architect, sparking the transformation from dense forest to open grassland. Fossilized soils show layers of charcoal that mark this turning point in Earth's history. What began as a random natural event grew into one of the most influential processes in ecology. Through fire, the planet learned to balance trees with grass, shadow with open light. Charcoal from old wildfires helped store carbon in soil for centuries. When wood burns incompletely, it leaves behind charcoal, a form of carbon that resists decay. Instead of releasing its carbon back into the atmosphere, this substance remains locked in the soil for hundreds or even thousands of years. Scientists call this biochar, and its presence can improve soil fertility while moderating climate by keeping carbon out of circulation. Forest floors around the world hold vast stores of this ancient charcoal, silent archives of past fires that still influence the chemistry of the earth. In recent years, researchers have begun recreating the process deliberately, using controlled burns to make biochar for sustainable agriculture. What nature discovered by accident, humanity now uses as a tool for balance. Each layer of charcoal beneath our feet is a reminder that even the residue of fire has purpose, storing memory and life within the soil itself. Fire can act as both a destroyer and a creator in every ecosystem. Nowhere in nature is duality more visible than in the behavior of flame. It consumes, yet it renews. It clears, yet it nourishes. In forests, prairies, deserts, and wetlands alike, the same process that devastates one generation prepares the ground for the next. Seeds that need heat to open, fungi that feed on char, and animals that follow the regrowth all depend on what first appears as ruin. Without fire, ecosystems stagnate and overgrow, losing vitality. With it, balance returns. Every blaze completes a cycle that mirrors creation itself, where endings and beginnings coexist. Scientists studying fire ecology find that even the timing and intensity of burns are tuned by evolution. The element that once terrified humanity is revealed as one of the oldest tools of life, shaping the planet's renewal with every spark that meets the air. Fire requires three elements: heat, fuel, and oxygen. Every flame, from candle to inferno, depends on a perfect triad known as the fire triangle. Heat initiates the reaction, fuel sustains it, and oxygen keeps it alive. Remove any one, and the process ends instantly. This balance explains why damp wood smolders instead of burning, or why flames suffocate under a blanket or foam. In controlled environments such as engines or furnaces, this principle allows precise manipulation of temperature and power. The fire triangle also symbolizes energy's dependence on harmony. Too much of one element can lead to chaos, too little to failure. Understanding this interplay gave humanity its earliest scientific insight into combustion. Every spark obeys it, from the smallest ember to the most distant star, which burns through its own version of this eternal equation. Fire, in all forms, is the art of perfect balance, sustained through chemistry. Removing any one of these stops combustion instantly. Fire survives only when its three vital elements coexist. If the heat drops below ignition temperature, the reaction ceases. If fuel is exhausted, nothing remains to burn. If oxygen is cut off, the chemical chain collapses. This principle forms the basis of firefighting and prevention. Water absorbs heat, foam smothers oxygen, and isolation removes fuel. The moment one side of the triangle disappears, the process cannot continue. In this way, even the fiercest blaze can be subdued through an understanding of its needs. The fragility of flame is hidden beneath its appearance of strength. It depends entirely on conditions, thriving only when nature allows. To extinguish fire is not to destroy it, but to unmake the circumstances that sustain it. A reminder that even the most powerful forces can vanish when balance is lost. Some reactions mimic fire without producing flame, such as rusting iron. Oxidation does not always glow or blaze, yet it follows the same principles that govern burning. When iron rusts, its atoms combine slowly with oxygen and water, releasing energy too gradually for light to form. Over time, the metal transforms into reddish oxide, a solid version of combustion stretched across years instead of seconds. The process proves that fire and rust are part of the single continuum of chemistry, separated only by speed. Even in the stillness of corrosion, the same exchange of electrons occurs, linking the quiet decay of metal with the brilliance of a flame. This slow fire shapes landscapes and industries alike, carving ships, bridges, and machines into powder. In both flame and rust, matter seeks equilibrium, releasing stored energy until it becomes stable once more. Phosphorescent reactions are chemical fires without heat. In certain reactions, energy is released not as warmth, but as light. This gentle glow, known as phosphorescence or chemiluminescence, appears in minerals, ocean creatures, and laboratory mixtures. Fireflies, for instance, produce light through a precise chemical reaction that wastes almost no energy as heat. The result is a cool radiance, a flame in essence, but not in temperature. In the deep ocean, countless organisms use this cold fire to communicate, hunt, or hide, painting the darkness with shifting constellations of blue and green. Scientists study these reactions to create efficient lighting and medical imaging technologies. They reveal that combustion is only one way for matter to shine. Within the chemistry of phosphorescence lies a peaceful counterpart to flame, light born from transformation but untouched by destruction. It is nature's quiet fire, glowing softly without consuming the world around it. Combustion in pure fluorine is far more violent than in oxygen. Fluorine is the most reactive element known, and when used as the oxidizer in combustion, it produces results beyond imagination. Almost any material, even substances that resist normal burning like glass or sand, can ignite when exposed to it. The reactions release enormous amounts of energy, often accompanied by blinding flashes and clouds of corrosive gas. Because fluorine bonds so eagerly with other elements, it can strip atoms apart in an instant. Scientists handle it with extreme caution, studying its properties in controlled chambers. In theoretical propulsion systems, fluorine could outperform oxygen as a fuel oxidizer, though its volatility makes it impractical for most uses. Its behavior demonstrates the outer limits of combustion chemistry. Fire in this form is no longer gentle or visible. IIT is pure reaction, the most intense expression of matter's desire to combine. Hydrogen burns with a nearly invisible pale blue flame. When hydrogen reacts with oxygen, It forms water vapor and releases heat, yet the flame it produces can barely be seen in daylight. The reaction is so clean that almost no carbon particles or glowing soot exist to color the light. The faint blue hue comes from excited molecules emitting photons as they cool. Because the flame is nearly invisible, hydrogen fires are difficult to detect without specialized sensors, posing unique safety challenges. Despite this, hydrogen is considered a fuel of the future due to its efficiency and abundance. Its combustion produces only water as a byproduct, making it one of the cleanest energy sources imaginable. The ghostly flame of hydrogen represents the quiet potential of chemistry harnessed without pollution, a whisper of energy that embodies both purity and power. Liquid oxygen can make organic materials explode on contact. When substances like paper, oil, or fabric touch liquid oxygen, they absorb it rapidly, becoming saturated with one of the most reactive elements in existence. If these oxygen-rich materials are then disturbed, even a small spark or friction can set off a violent explosion. The reason lies in chemistry. The stored oxygen feeds combustion so quickly that energy is released in a fraction of a second. Engineers who handle rocket fuels or cryogenic systems must take extraordinary precautions to prevent such contact. In spaceflight, liquid oxygen serves as an oxidizer, enabling engines to burn at extreme temperatures. Yet outside those systems, its touch is perilous. It turns ordinary matter into potential fuel, waiting for the smallest trigger. This combination of beauty and danger defines much of fire's nature. A delicate balance between creation and catastrophe. Sodium burns bright yellow because of its atomic spectrum. When sodium atoms are heated, their electrons jump to higher energy levels and fall back again, releasing photons at a specific wavelength. That wavelength corresponds to a deep golden yellow, one of the most recognizable colors in all of chemistry. The same spectral line that colors streetlights and fireworks also appears in laboratory flames when sodium is present, even in trace amounts. The process reveals the intimate relationship between fire and quantum physics. Every element emits light according to its own atomic structure. This signature allows scientists to identify substances by their color, using fire as a spectroscope long before modern instruments existed. The glow of sodium is both a tool and a symbol of order within chaos. Inside the seeming randomness of flame, the universe reveals its precision, turning energy into light of perfect and predictable beauty. Different metals create distinct flame colors used in fireworks. Fireworks are painted with chemistry. Strontium salts produce deep reds, barium gives green, copper creates blue, and sodium glows yellow. When heated, the atoms in these metals release photons at characteristic wavelengths, producing the vivid palette that fills the night sky during celebrations. Each color requires careful balance of temperature and composition too hot, and the hue washes out into white. Ancient alchemists first noticed these variations while heating minerals in their furnaces, but it was modern science that turned the observation into art. Today, chemists design fireworks with astonishing precision, using oxidation, reduction, and flame temperature to choreograph explosions of light. The spectacle is more than entertainment. It is chemistry expressed as beauty, a reminder that even the most joyful bursts of color come from the controlled mastery of fire's elemental language. Fireworks are precisely engineered explosions of powdered chemistry. Inside every firework shell lies a carefully arranged system of fuel, oxidizer, and color-producing compounds. When the fuse ignites, a timed sequence of reactions launches the shell skyward, then detonates it at a precise altitude. The explosion spreads burning pellets, or stars, across the air, each glowing with color based on its chemical makeup. Engineers calculate the size, pattern, and delay of each burst using mathematics and pyrotechnic science. Even the sound of the explosion is designed through casing thickness and composition. Though their beauty lasts only seconds, fireworks represent centuries of experimentation in combustion and control. They are among humanity's purest collaborations with chemistry, transforming simple powders into moments of wonder. Every brilliant bloom that fades against the dark sky is a reminder that knowledge and artistry can coexist perfectly within the heart of fire. Candle flames contain countless micro-explosions every second. To the naked eye, a candle flame appears soft and continuous. Yet under high-speed photography, it becomes a field of endless microscopic detonations. Each glowing particle of carbon ignites and extinguishes in fractions of a second, releasing bursts of light and heat before vanishing into invisible gas. These miniature explosions are the essence of combustion, countless tiny events merging into what looks like steady fire. The sound they make is too faint to hear, but together they produce the gentle shimmer and flicker we find so hypnotic. Every moment, new molecules form, break apart, and reform in a perfect rhythm that sustains the flame. What seems calm and still is, in truth, a storm of chemical motion, a quiet orchestra of reactions dancing just above the wick. In its delicate glow, the candle hides a universe of restless energy. Soot is carbon that escaped complete combustion. When a flame burns without enough oxygen, not all fuel molecules can fully react. The leftover carbon condenses into tiny black particles known as soot. These microscopic grains rise through the hot air, glowing orange for an instant before cooling into dark smoke. In ancient times, soot collected on the ceilings of caves and temples, marking the first record of human fire use. Artists later ground it into ink and paint, transforming residue into beauty. Though small, soot affects everything from air quality to climate, absorbing sunlight and warming the atmosphere. Its presence tells a story of imbalance, fire deprived of breath. Scientists study how to reduce soot in engines and stoves to make combustion cleaner and more efficient. Each particle is a fragment of incomplete transformation, a reminder that even in flame, perfection depends on harmony between fuel, heat, and air. A flame's shape reveals the speed of its chemical reaction. Every flame is a living graph of chemistry. The sharper and more elongated the flame, the faster the reaction is occurring. In a calm candle, the flame tapers smoothly upward as hot gases rise and fresh oxygen flows inward. In an explosive burn where fuel and air mix violently, the flame expands into jagged patterns or even shockwaves. Scientists use high-speed cameras and spectroscopy to study these forms, reading their motion like language. The curves, flickers, and edges all encode information about the velocity of molecules and the transfer of heat. Even small variations in air pressure or humidity can change the entire structure. What the eye sees as beauty, science reads as data. A flame's shape is a signature of its energy, a fleeting portrait of matter in motion, drawn in light and erased by air within the span of a breath. In microgravity, flames form perfect spheres of diffusion. Without gravity to pull hot air upward, a flame no longer flickers or stretches. It becomes a glowing sphere, steady and symmetrical, fed only by the slow diffusion of gases. Inside space stations, astronauts have studied these spherical flames to understand combustion in its purest form. The shape reveals how fire behaves when freed from convection, where heat does not rise and cool air does not fall. The result is almost silent and still, like a miniature sun floating in air. These spherical flames burn more efficiently and at lower temperatures than on Earth, offering clues for cleaner engines and fuel systems. Watching them drift in microgravity is like observing a living star, suspended between chemistry and art. In that weightless chamber, the laws of fire are rewritten, showing that even the simplest spark becomes something cosmic when gravity releases its hold. Scientists study spherical flames to understand how fires spread. In the weightlessness of space, flames reveal their secrets. When confined in microgravity, the absence of upward flow allows researchers to see combustion in slow motion, exposing the fine details of how gases mix and reactions propagate. By studying spherical flames, scientists can model how fire travels through different materials and environments on Earth. These experiments help improve spacecraft safety and also guide advances in energy efficiency, engine design, and pollution control. The even burn of a spherical flame shows what happens when convection is removed and only molecular diffusion carries oxygen to fuel. It is the purest version of fire, stripped of turbulence and chaos. Observing its smooth glow, researchers witness the fundamental language of combustion, the same processes that shape stars, engines, and even the flicker of a simple candle at home. Under high pressure, even carbon dioxide can support combustion. At ordinary conditions, carbon dioxide extinguishes fire, smothering flames by displacing oxygen. Yet under immense pressure and extreme heat, the molecule can behave very differently. Experiments have shown that in certain mixtures, carbon dioxide can break apart and release oxygen atoms that sustain brief flashes of combustion. These reactions occur in conditions similar to those deep inside planets or during high-energy industrial processes. The discovery challenges the simple view of carbon dioxide as a passive gas, revealing its potential to become reactive under stress. Studying these phenomena helps scientists understand atmospheric chemistry on distant worlds, where pressure and temperature far exceed anything on Earth. Even the most stable compounds can reveal hidden power when pushed to their limits. In the deep language of physics, no element is ever entirely dormant, only waiting for the right conditions to awaken. Flames can act as ion engines that push tiny particles of air. Inside a flame, gas molecules break into charged particles called ions and electrons that respond to electric fields. When a current is applied, these charged particles accelerate, creating a small but measurable thrust. Scientists call this ionic wind, and it can move objects lighter than a feather or drive air through micro-engines. The same principle powers some spacecraft propulsion systems, where ionized gases are expelled to generate steady motion in the vacuum of space. In laboratory settings, electric fields can even shape or bend flames, guiding them like threads of light. Each flicker becomes both chemical reaction and electrical phenomenon, a bridge between heat and motion. Though invisible to the eye, these gentle pushes reveal that fire is more than light and warmth. It is a plasma in motion, capable of exerting force and carrying energy in ways that hint at the future of propulsion. Cold flames burn slowly and silently at low temperatures. There exist flames that glow faintly blue and feel almost cool to the touch. Known as cold flames, they occur when fuel and oxygen react so gradually that the temperature stays below normal ignition levels. They are nearly invisible and emit little heat, yet they represent true combustion. In engines and chemical reactors, these delicate reactions often appear as an intermediate stage before full ignition, revealing how burning begins. Scientists study cold flames to improve fuel efficiency and reduce pollutants, since they show how to achieve energy release with minimal waste. Their discovery proved that fire does not need roaring heat or bright light to exist. These quiet, ghostly flames demonstrate the subtlety of chemistry, a gentle rearrangement of molecules that whispers instead of roars. proving that transformation can happen even in stillness. Fire can turn sand into synthetic stone called vitrified rock. When exposed to intense heat, sand and soil can melt into a glass-like material known as vitrified rock. This transformation occurs naturally where lightning strikes or lava flows, and artificially in furnaces or explosions. The heat fuses silica and minerals together, forming smooth, glossy surfaces that cool into solid stone. Archaeologists have found vitrified walls in ancient fortresses across Europe, suggesting that entire ramparts were once subjected to deliberate burning, perhaps as defense, ritual, or warfare. The resulting material resists erosion and remains fused for millennia. In modern science, similar techniques are used to create durable synthetic stone for construction and waste containment. Each piece of vitrified rock tells a story of transformation, where the raw earth was briefly turned liquid by fire and then frozen in that moment of change, a permanent memory of heat made visible. Lightning strikes can magnetize soil through intense heat. When lightning hits the ground, temperatures soar higher than the surface of the sun for an instant. The soil and minerals in the strike zone melt and fuse into glassy tubes called fulgurites. Within these fragile structures, iron-bearing minerals align as they cool, locking in a faint magnetic field created by the lightning's electric surge. Scientists can study these magnetic traces to learn the direction and intensity of ancient strikes, effectively reading the history of storms recorded in stone. The process also alters the chemistry of the soil, creating compounds that would never form under ordinary conditions. Each fulgurite is a frozen path of energy, a sculpted memory of sky meeting earth. To hold one is to touch the residue of an event that burned hotter and faster than anything the human hand could ever create. Stars are cosmic fires powered by fusion instead of oxygen. The light of the stars comes not from burning fuel in air, but from the merging of atomic nuclei deep within their cores. Under immense pressure and gravity, hydrogen atoms fuse into helium, releasing colossal amounts of energy as radiation. This process, called nuclear fusion, is the same principle humans attempt to replicate in experimental reactors on Earth. The energy that keeps stars shining for billions of years is the same energy that powers all life here. Fire on Earth rearranges molecules, but fire in stars reshapes atoms themselves. Each sunrise is a direct gift of fusion, a reminder that our planet orbits a living furnace, vast beyond imagination. When we look at firelight, we are seeing a faint reflection of the same physics that burns in the hearts of stars, a universal language written in heat and brilliance. Some planets rain flammable chemicals that could ignite with a spark. On worlds like Saturn's moon Titan, the atmosphere is rich in methane and other hydrocarbons that condense and fall as rain. Rivers and lakes of liquid methane carve landscapes beneath orange skies. If oxygen were present, this world would erupt in flame, its entire surface a sea of fire. The absence of oxygen keeps it calm, a frozen mirror of chemistry waiting for the right trigger. Scientists study such environments to understand how planets evolve and how their atmospheres behave under alien conditions. The paradox of a place that rains fuel but never burns captures the strangeness of the cosmos. Titan's gentle rain reminds us that fire is not a constant in the universe. It is a delicate balance between the right elements, the right pressure, and the invisible moment when reaction begins. Volcanoes on distant moons erupt with sulfur flames. On Io, a moon of Jupiter, volcanoes blaze with yellow and blue plumes of molten sulfur, glowing across the frozen darkness of space. The eruptions are driven not by sunlight or seasons, but by tidal forces, as Jupiter's immense gravity stretches and kneads Io's crust, generating heat from friction. When sulfur gas escapes and ignites, it burns in eerie colors rarely seen on Earth. Spacecraft that have photographed these eruptions show fountains of glowing material rising hundreds of kilometers high. The Moon's surface constantly renews itself under this alien fire, making it the most volcanically active body in the solar system. Watching these distant flames is like witnessing creation in another language. They prove that fire is not confined to Earth, but thrives wherever energy and chemistry collide in the vast machinery of the cosmos. The Sun's corona blazes at millions of degrees. Surrounding the Sun is a faint halo of light called the corona, visible during eclipses or through special instruments. Though farther from the core, it is astonishingly hotter than the solar surface, millions of degrees compared to the mere thousands below. Scientists believe magnetic fields twist and snap there, releasing immense bursts of energy that heat the gas to unimaginable temperatures. The corona constantly streams charged particles into space, creating the solar wind that shapes planetary atmospheres and paints the northern lights across Earth's poles. It is a fire beyond fire, invisible most of the time, yet it touches every atom of life on our world. To look upon the corona is to see the boundary between matter and pure energy, where the Sun whispers its light across the solar system. Meteor impacts can set forests alight even after the object vaporizes. When a meteor enters the atmosphere, it compresses the air in front of it, generating shock waves and heat that can ignite forests before the rock itself touches the ground. Even if the meteor burns away completely, the blast of superheated air can trigger widespread fires across vast distances. Evidence of this can be found in layers of charcoal preserved in ancient sediments, marking impact events that altered climates and reshaped ecosystems. The Tunguska explosion in Siberia, for example, leveled thousands of trees without leaving a crater, its fiery wave sweeping across the wilderness. Such events remind us that fire from the sky has long influenced Earth's history. Each streak of light across the night carries both wonder and devastation, connecting the silent motion of celestial bodies with the fragile balance of life below. Nebulas glow with radiant energy similar to a vast cold flame. In the depths of space, immense clouds of gas and dust stretch across light years, shining with the faint glow of ionized atoms. These nebulas are not hot enough to burn as stars do, yet they emit light through the same principles that make fire glow. When ultraviolet radiation from nearby stars excites the gas, it releases photons in soft hues of red, green, and violet. The result is a flame that seems frozen, a tapestry of light without heat. Within these clouds, new stars and planets are born, shaped by gravity and time. To gaze upon a nebula is to witness creation unfolding slowly across the ages. It is the universe breathing in color, a fire too vast to touch, painting the silence of space with light that has traveled for thousands of years. On Titan, methane could burn if oxygen ever reached its atmosphere. Titan's skies are thick with orange haze, and its rivers flow not with water, but with liquid methane and ethane. If oxygen were somehow introduced into this world, even a single spark could ignite the entire atmosphere. The planet would become a global flame, consuming itself in a flash of chemistry. Scientists use this scenario to study how fragile the balance of life-supporting conditions can be. On Earth, the same reaction powers engines and furnaces, but on Titan, it exists only as potential. The idea of a world that could ignite if the wrong element appeared reveals how specific the ingredients of stability truly are. In the silence of Titan's frozen plains lies a sleeping fire, proof that combustion is not merely destruction but possibility waiting for the right breath of air. Fire from re-entry heats spacecraft surfaces until they glow, When a spacecraft returns to Earth, it enters the atmosphere at tremendous speed, compressing the air in front of it so violently that the gas heats into plasma. Temperatures soar high enough to make metal glow white-hot, creating a fiery envelope around the vehicle. The light we see streaking across the sky during re-entry is not burning fuel but superheated air radiating energy. To survive, spacecraft use heat shields that absorb and shed this heat, layer by layer. The process mirrors natural meteors, but is controlled and deliberate, a conversation between human engineering and the raw power of physics. Each descent is a kind of rebirth, a plunge through light that recalls the earliest sparks of creation, where motion itself becomes fire and the sky folds open to welcome its return. Plasma arcs in lightning resemble miniature solar flares. Every lightning bolt is a brief but powerful surge of plasma, the same state of matter that fills the sun's atmosphere. In that instant, air becomes electrically charged gas, glowing as electrons leap between atoms. The temperature can exceed that of the solar surface, and the energy released is enough to power cities for moments at a time. The branching patterns of lightning mirror the magnetic loops that shape solar flares on a colossal scale. Both are born from electric fields snapping under stress, releasing their energy in sudden bursts of brilliance. Observing lightning up close offers a glimpse into the same forces that rage across stars. Each flash is a reminder that the fire of the heavens is not distant. It lives within our sky, pulsing between cloud and earth, like the breath of a living cosmos. Every flame on Earth is a faint echo of the stars that forged its atoms. The carbon, hydrogen, and oxygen that feed every fire were born billions of years ago in the cores of ancient stars. When those stars exploded, they scattered their elements through space, seeding the gas and dust that would one day become Earth. Each spark we light continues that original fusion, the same transformation of matter into energy that began in the heart of the cosmos. A simple candle connects us to the life cycles of suns long vanished. Its light carries the memory of explosions beyond imagination, condensed into warmth we can hold in our hands. Fire is not merely a human discovery, but a cosmic inheritance. Every flicker in the dark is the universe remembering itself, burning quietly in miniature, whispering the story of its own beginning. As the light of the last flame fades, the mind begins to soften. You have wandered through the secret chemistry of fire, through sparks that whisper the language of the stars and embers that carry the memory of creation itself. Each flicker has been a reminder that what burns is never truly lost. It only changes form, finding new ways to glow. Fire is a teacher of transformation. It shows us how energy moves, how stillness hides motion, and how every atom carries a story older than time. The same forces that warm a candle's edge ignite the hearts of suns, shaping everything we see and everything we are. To watch fire is to witness the universe remembering itself, transforming endlessly from one shape of light to another. Now the warmth begins to settle. The body grows heavy, the breath deepens, and the thoughts slow to an ember's quiet rhythm. The room around you fades into the softness of shadow, while the echo of fire continues somewhere far away, in the hush between worlds. Let yourself drift with it. Feel the calm that follows every spark, the stillness that holds the memory of flame. Somewhere beyond sight, the stars are still burning, their ancient light flowing through the dark. It reaches you even now, gently, like a final spark finding its way home. If you happen to still be awake, you can go ahead and watch the next video now. But if your eyes are already closing, let the glow fade completely and rest in the warmth of the quiet that remains. The fire is still out there, watching over everything, and it will be waiting when you wake. Good night.